So I don't know how many of you were here yesterday or how many of you who weren't here yesterday did watch the video, but I had intended on doing double displacement reactions, which includes precipitation and neutralization reactions, and then today doing single displacement. But it took a little longer than I expected. And so today I'm going to start with double displacement, focusing on neutralizations, and then I'll go to single displacement. Okay, and it's 4 o'clock, so I'm going to go ahead and get started, but I'll keep letting people in. So there are 5 reaction types, and for 2 of them, the first 2, synthesis and decomposition, you would need to be told what the reactants and the products were. And you could be told, like, this thing is formed from its elements, or this thing decomposes into its elements, and then you'd figure out what the elements are. But pretty much you're told what the reactants and products are for synthesis and for decomposition. For combustion, you're told what the fuel is, and then you know to add oxygen and what the product should be, carbon dioxide and water. For single displacement and double displacement, you need to predict products, and you also have to predict if the reaction happens. For single displacement and double displacement, those reactions happen in water, and so it's aqueous chemistry, and we need to use our table of solubilities. So just in case you weren't here yesterday, let me show you where to find things. So here we are on the home page. Double displacement reactions were the notes from yesterday. I have 3 more slides to go through, and here's the table of electrolytes. The table of electrolytes will be useful as you do the exam, do the lab this week. There's no exam this week. See, I don't know why it's not showing me. There we go. So the table of electrolytes looks like this, and we're going to use it for what we did yesterday, and we're continuing today, double displacement, and also for single displacement reactions. Either in the video from yesterday that you can watch, or you were here yesterday and so you saw this. The steps for writing net ionic equations look like this. We start by predicting the products for the molecular equation, and the molecular equation is just the regular balanced chemical equation that we use for stoichiometry. And then to find the total ionic equation, we're going to use the solubility rules that are found on that page I just showed you. And then finally, the goal is to come up with a net ionic equation, which is just the equation of the chemistry that happened in water, what actually changed. And so there's a couple steps for that. So I'm going to continue what I started talking about yesterday. Yesterday, we looked at the double displacement reactions where the cation of the first combines with the anion of the second. And if they stick, either because it forms water or a solid, insoluble solid is formed, then a reaction occurred. The cation of the second combines with the anion of the first, and if they stick, then we have either a neutralization or precipitation. And you can have both reactions happen at the same time. So I focused on precipitation yesterday and in that video, and we didn't quite get to neutralization. So I want to do 3 of those now, and then we'll get to single displacement. So the first thing for predicting products for double displacement is to correctly write the formulas. Solutions of barium hydroxide. So I know barium's a group 2 metal. It has a +2 charge as an ion. Hydroxide has a -1 charge. It's a polyatomic that I memorized. And perchloric acid. Ic acid come from 8s. And if it's a per 8, it's because there's 1 oxygen more. To make it an acid, I add enough hydrogen so that it's neutralized. Its net charge is 0. So here's perchloric acid. So I write my reactants. And then we predict products. First thing you need to notice is that we have a base and an acid. So this is an acid-base reaction. We're going to form a water and salt. What kind of salt? Salt just means ionic compound, so there's a lot of salts. And then I'm going to look at the cation of the first and the anion of the second. We don't really have an anion for acid, but we're going to kind of break it apart in our head and remember how that acid was named. So we're kind of undoing the nomenclature. to see perchlorate is the negatively charged ion there. Perchlorate has a charge of -1. Barium is a +2. I'm going to need 2 perchlorates. Do that same idea, but now with the other, the other possibility, and that is the cation of the first and the anion of the second. So acid plus base makes water and salt. Our salt is barium perchlorate, and water is H2O. But I'm not going to write it H2O when I do acid-base reactions, especially at first. I'm going to write it H-OH. And this is to remind myself that one hydrogen came from the acid, and the other hydrogen is part of a hydroxide, and the hydroxide came from the base. And so I look at the acid that I have, perchloric acid, and I look at the base I have, barium hydroxide, and I ask myself, how many waters could be made? Well, barium hydroxide could make 2 waters because it has 2 hydroxides. But perchloric acid just has 1 hydrogen. If I have 2 hydrogens, I can make 2 waters. So for an acid-base reaction, I always start by looking at the acid and the base and saying, what is the lowest common multiple? How many waters could I make? And then I remember that water has 2 kinds of hydrogens, the hydrogens that came from the acid and the hydrogens that came from the base. Once I do that, the salt just works out. So I need to make sure this is a balanced chemical equation so that I have the right coefficients, and I can do that with a t-table, or I can do it in my head. This is a balanced equation. So right now I have a balanced molecular equation, and that is the starting place for writing the total ionic and the net ionic. To write the total ionic, I need to look at all these species and decide, do they stay together or are they ionized? Do they break into ions in water? And so to do that, I'm going to go to my table of electrolytes. And there's 4 areas on this table. We have acids. There are only 6 strong acids, and a strong acid is a strong electrolyte. What that means is it's strong enough to ionize or be ionized by water 100%. It completely dissociates into ions. There are only 6 strong acids, and perchloric acid is one of them. And then we have a category of bases. Group 1 and group 2 hydroxides tend to be strong bases. And then all the other hydroxides are insoluble. So strong bases are strong enough to stand apart, and they dissociate 100% in water. Then there are salts and molecules. So I see that perchloric acid is a strong acid. That means it's going to be ionized. I see that barium hydroxide is a strong base, and so it's going to dissociate into the ions that it's made of. Our salt was barium perchlorate, and it isn't listed. There's no rules about that. So I'm just going to tell you it is a strong electrolyte. It breaks apart. And I wouldn't give you that one on a test because you don't have a rule for it. Okay, when I break these things apart, I have to remember how many ions they were made of. So barium hydroxide is made of 1 barium ion and 2 hydroxides. Oops. Perchloric acid was a strong acid, so 2 hydrogen ions and 2 perchlorates. Stop. This is a strong electrolyte, barium perchlorate, even though you don't know that. We're going to break it apart. And now I'm going to write water like we normally see water. So now I can say 2H2O and give it a state symbol. Solid, liquid, gas, and aqueous are our state symbols. And if something is aqueous, you don't need to state it because we'll be writing that over and over again. Okay, so now I have a balanced total ionic equation. To get to the net ionic equation, I'm just going to cross out anything that is exactly the same on the left and the right. Like here we have barium as a free-floating ion with a +2 charge. And then perchlorate, 2 perchlorate on the left and 2 on the right. And then I am going to rewrite whatever I didn't cross out. Now I notice that all my coefficients are even, and a balanced chemical equation in our class is the lowest whole number ratio of reactants to products. And so I'm going to divide 3 by 2 and put a box around it. That's my answer. Hydrogen ion plus hydroxide react to form water. This is the net ionic equation when we have a strong acid. Perchloric acid is one of the 6 strong acids, and a strong base. Okay, so this time we have a strong base, calcium hydroxide, but with a weak acid, and it's going to look a little bit different. Go ahead and write the formulas for calcium hydroxide and acetic acid, and then predict the products and add coefficients to balance the equation. Sometimes when students are doing this, they come up with some crazy things. For example, I have seen this before as a formula for water. Does that make any sense? Why would a student do that? Because that's how it kind of looks over here. So for an acid-base reaction, the first question I ask myself is, this acid, this base, how many waters could they make? Calcium hydroxide could make 2 because there's 2 hydroxides in each formula unit. Acetic acid could make 1 because there's only 1 acidic hydrogen, only 1 hydrogen on the left at the front. But if I put a 2 here, I can now make 2 waters. And the salt works out. 1 calcium on the left, 1 calcium on the right. 2 acetates on the left, 2 acetates on the right. 2 hydroxides, 2 hydrogen ions would make 2 waters. So now I'm going to use my solubility table or table of electrolytes to decide what stays together, what breaks apart. I look up calcium hydroxide and I see that it is a strong base, strong enough to stand apart. It breaks into 3 ions. Acetic acid is an acid, and I see that it isn't one of the 6 strong acids. If it is a weak acid, it doesn't dissociate much, and we write the formula. We write the formula in the net ionic and total ionic equations, which means don't break it apart.
Sue, I have a question real quick.
Yeah.
On solubility rule number 2, it has acetic acid with no exceptions.
No, it has acetate ion.
Oh, okay.
And those rules are only for salts, and this isn't a salt. Salts are ionic compounds, and this is a covalent compound.
Okay, thank you.
Yeah. I'm glad you mentioned it, because that's actually a very common source of confusion. But now we need to use that rule, because calcium acetate is a salt, and acetates are soluble, no exceptions. And I'm going to write water the correct way and add an L for liquid. Okay, so I want us to imagine what's going on here for a second. What we have is, I have a beaker here. And in the beaker, or I have a jar, is calcium hydroxide. And the calcium and the hydroxides are floating around. It might have been a powder, like somebody may have taken a scoop of powder and put it in there, because things that are ionic can exist as solids or aqueous. They never are liquids or gases at room temperature and pressure. But once they put it in, the ions fall apart. Water pulls them apart into the ions that they are. And then over here, we have acetic acid. And in water, it's floating around mostly stuck together. There might be a few of these that break apart into hydrogens and just acetate ions, but they stick together as a molecule. When we mix them, we're sticking them in one container. And when they're in the one container, the hydroxide, which is a strong base, is able to pull that hydrogen ion off. So it's like acetate and hydroxide are competing over that hydrogen. And when acetate is alone with the hydrogen, it's strong enough to hang on to it. But in competition with hydroxide, hydroxide is able to make that reaction happen. So what's happening on the left of the reaction is we have one bottle of this and a different bottle of that. They haven't been allowed to mix yet. But once they're allowed to mix and they're in the same space, that's when chemistry can happen. And that's when there's sort of a competition for who gets what. Okay, so we have a balanced reaction, and this time we had a strong base, strong enough to pull that hydrogen off, strong enough to stand alone by itself, but also able to react with the hydrogen, and a weak acid. Wa is for weak acid. When we have a weak acid, we have to leave it together. So now we're going to write the net ionic equation by canceling any spectators that there are. The only spectator I have is calcium ion. Calcium is a free-floating ion on the left and on the right. But the acetate on the left is part of an acid, and the acetate on the right is a free ion. And so those are different. We don't cancel them. Okay, I noticed that I have a lot of 2's. So I'm going to rewrite my equation. But first I want to cancel this 2, 2, 2, 2. Those can all become 1's. When we make sure that an equation is balanced, there's 2 things we check. We check mass balance, and that means we look at the reactant and the product side and make sure that we have the same number of each kind of element. So we're looking at them like atoms. And then we do charge balance. And charge balance means the net charge on the left has to equal the net charge on the right. Yesterday, when I did precipitation reactions, it just worked out that we always had 0 on the left and 0 on the right, but that's not going to be true this time. Okay, so I'm going to start adding things up. How many carbons on the left? 2. On the right, 2. Hydrogens on the left is 1 plus 3. Hydrogens on the right. Oh, no, I'm sorry. 1 plus 3 plus 1. 1, 3, 1. And on the right, it's 3 and 2, so that's also 5. Okay, for oxygens, it looks like 3 on the left, 3 on the right. Oh, there's no calciums. Now for the charge, I'm just looking at the net charge here. Hydroxide has a -1 charge. Acetic acid is a molecule, a compound, so it's neutral. The charge on the left is -1. And then there's an arrow. Acetate ion has a -1 charge, and water is neutral. So we have -1 on the right, -1 on the left. This is a balanced equation. The reason that it isn't 0 and 0 on both sides is because it's a net ionic equation. So for the molecular equation, it would be 0 and 0 on both sides. For the total ionic, it would be 0 and 0 on both sides. But when we cancel the spectators, which are present, but not doing chemistry, we can have a non-zero charge. Okay, and here's our last one. And this one is super important because it has sulfuric acid, and sulfuric acid is just a little bit different. So notice that sulfuric acid is one of the 6 strong acids, which means it is going to ionize. But then there's this fine print here that says first proton only, which means when we go to the ionic equation, we take off a hydrogen, but we still have a hydrogen sulfate. So maybe highlight that on your table of electrolytes so that you're not caught off guard by that when you do assignments, when you do practice. Ic acids come from 8s. Because of the -2 charge, we need 2 hydrogens.
Hey, Sue, can you go back to your notes?
You want to see what I'm doing? Like that?
Yep, thank you.
I'm glad you guys are here to correct me. Thanks for talking to me, AJ, because I could see what I was doing. Okay, so the first question I asked myself is, how many waters can this base make? And the answer is 1. How many waters can the acid make? 2. Why don't I put a 2 in front of potassium hydroxide and make 2 waters? Potassium hydroxide is a base. Is it a strong base? Yes. All group 1 hydroxides are strong bases. So it breaks into ions. The 2 applies both to the potassium and to the hydroxide. Sulfuric acid is a strong acid, but it says first proton only. So when I break it apart, I pull off 1 hydrogen ion and I have a hydrogen sulfate ion left over. Acid plus base makes salt plus water. What's our salt here? Our salt is potassium sulfate. Is there a rule for that? So for salts, it says use solubility rules, and the solubility rules are the ones at the bottom. So there is rule number 1 says potassium salts are soluble, which means they dissolve, and if it's ionic and dissolve, it breaks into ions, it dissociates. Rule number 4 says that sulfates are soluble except, and then it names 5 cations, but this isn't one of those. So our salt is soluble. When we do this, we have to remember that this 2 here in the formula is saying 2 of those monatomic cations, but this 4 is part of a chunk of charge and it stays there. I have seen students do this and it's wrong. That happens every semester. And then sometimes they think, well, I have 2 plus 1, so maybe it's a 2 plus. It's still wrong because this is not an ion that you have learned. So there's 2 kinds of subscripts and we need to be aware of that. Then when I write water, water is a covalent compound and it's on this table. It's molecular. It's not an electrolyte, which means it doesn't have charge. And water is our first one. I suggest to this table that you add sulfur dioxide because that's a gas forming product that's going to happen sometimes, SO2. Okay, that's a balanced total ionic equation. We could check charge and mass if we wanted to. And now we're going to cancel out spectators. I see potassium ion, 2 of them on the left and the right, but everything else stays. Okay, so that was us finishing up double displacement reactions from yesterday.